what we have again over here is the decoder network. Am I any like, do I have any questions or anything, or do I continue with the decoder architecture as well?
Go
Hello?
ahead. Yeah, go ahead.
Okay, thank you, sir.
Keep continuing.
We will
Yeah.
go over to the decoder architecture, this entire part, and I'll just give a small brief of what there lies. We understood what multi-head attention is. Now we'll go a little step ahead into what's masked multi-head attention, and then adding and normalizing every single feature that we'll be receiving from that matrix. And then again, adding and normalizing feed forward, and finally passing it through a linear and a softmax function to get the final output probabilities of every single token parsed into the LLM. Decode architecture. What's MMHA actually? Masked multi-head attention. We understood what is query, we understood what is key, we understood what is value. For every single of this, we apply a small mask to prevent that addition into future positions. I would love to go into the like the exact mathematics or the exact linear algebra of this, but that would essentially consume a lot more of time, and I actually would deviate the course of the presentation. So I've just kept it in smaller terms, that it contains all the it performs multi-head attention and then concatenates them. It's like a concatenation of MHA, multi-head attention. Over every individual matrix obtained, it performs MHA over that and then concatenates. Over here, if you can see head 1, Q1 equal to K1 equal to V1 is the input matrix. We find the QKT, W1 is the softmax of A1, that's A1 divided by root over of DK. And over here, if you can see, once when we put the masking essentially means taking any random elements present in that vector and like bring it down all to 0, so that there's this mask or a single iteration of or a single like cloth that actually acts as a garb over that particular element. Then we again go to O1 is equal to W1 dot product of V1, and every of these heads are then concatenated. Apply learnable linear transformation, and it's a masked multi-head attention with 2 heads. Now we come to this second ontology, the second description of what LLMs are. Like this, we have this entire segment called pre-training of LLMs. That's essentially using language modeling. We have masked language modeling, then we have next sentence prediction. The second half after masked multi-head attention is the next sentence or the next word prediction. For example, if I'm writing, we have all have read that same, that simple email when we write in our Gmail boxes. We are writing a particular mail, and then the email prompt that comes up with a new, the next predicted word. So how does that come in? And the consecutive maths just behind that. Applies a small softmax layer to convert the scores into probabilities for every single word that the model has learned right now. And then the word with the highest probability is predicted out. This is like very over the crim explanation of what is next word prediction. But again, like over time, we will be again coming it into autoregressive and auto-encoded language modeling as well. So that's when we will learn in much more detail about how pre-training occurs and how masked multi-head attention and next word prediction are much more important than the credit we offer them. This actually essentially completes our decoder architecture. And if we again come over here, we have the same adding and normalization layer posed by the feed-forward network. We have the MMHA, the multi-head attention, and the feed-forward that essentially predicts the next word. Over here, the black box completes itself. And after this, we have an idea or a probability score of which word or which sentence or which token to generate next, which is then parsed off to the softmax layer to get the final probability. Throughout like my time when I was working, when I was researching, when I was trying to figure out things, I found this one question offered to me, that since we are working with biomedical data, since we are completely immersing ourselves into biomedical data with our entire project title being drug target discovery, that is, we need to read a lot of papers, we need our LLM, our chosen LLM, a lot of papers to understand the intricacies of those papers and finally have its own predictive abilities for the queries that will be passed on by the user. For example, we always wanted to have one multimodal LLM that could parse in all of your queries and given the absolute specific answer that could be used either by scientists doing drug discoveries or researchers or genetic researchers and lot more. Why? Then this question always occurs to me. This question I was asked as well, which one to use? As I just showed in my previous slides, there have been multiple LLMs being brought out by multiple companies, be it Perplexity, be it Anthropic, be it OpenAI, be it Google, Meta, everyone has their own LLM, and every single LLM has its own particular use case. We can't, essentially, it's like comparing apples and oranges, to be very frank and honest, but still every LLM has its specific use case. And I'm like trying to focus on just two LLMs, and I'll just try to compare of their architecture and say why for specific information retrieval from specific documents, there always lies a trade-off between these two, BERT and Llama. BERT essentially came out in 2016, Google bought it, and Llama bought by Meta in quite recently. It was in 2019 or something. I'm not sure of the date. But BERT follows the transformer, the standard transformer architecture, also again explained by the same 2017 paper. And Llama focuses on a self-attention architecture. If you can see over here, self-attention grouped multi-query attention with KV cache. All of these three vectors, the query, key, and value vector that we just understood, by multiplying the input embeddings with their respective weight vectors, are parallelly passed into a SHA, then normalized and feed forward, and finally again given into a normalization, and that's the final output. And this one is the transformers architecture. So why is this single architecture better or worse than like I can never say better or worse, but for our specific use case, which is like more usable or which offers a better understanding or a better useful case? I chose BERT, and my reasons are right over here. BERT has established performance and multiple more citations than Llama. This might also be because BERT is relatively older and researchers have had their time understanding the architecture and the entire depiction of why BERT works, of fine-tuning BERT and making specific models of BERT, be it BERT for common sense question answers, or be it Roberta BERT, be it Aristo BERT, and for like common sense question answers or day-to-day or scientific question answers or even biomedical question answers. We have everything. But for Llama, no such existing, I wouldn't say no such, but less such existing work has been done. Robust fine-tuning, BERT offers this entire fine-tuning architecture for domain-specific tasks and a stronger community support owing to be like Google has one of the highest engineers, of course, and has been cited by much more people. Llama, on the other hand, is apparently computationally efficient, and it's much better for resource-constrained environments, only because all of these three vectors are parsed in parallelly to the single head attention model. Over here, we were using multi-head attention, and every single like of these vectors, Q, K, and V, were parsed in one by one. And then there was the softmax layer, then there was this O value formation, and then multiple such O values were concatenated to form the masked multi-head attention, which takes much more time and much more computation power, not available on our local laptops, of course. Llama solves that problem, takes everything in at parallelly, resource constraint, for resource constraint it's damn good, and it can also handle large data sets. But why we face difficulties? Because existing Llama research has not been fine-tuned over specific data sets pertaining to our corpus. For example, if I need a model specifically only for biomedical data set, I won't have a Llama model fine-tuned to that. I am essentially required to do that on my own, and that would require a lot of computation, lot of computational power, lot of architecture handling, and a lot more. On the other hand, BERT has actually, there was actually a research by Korea, University of Korea, and they proposed BioBERT, which is something again I'll be proposing just in the next slide itself. BioBERT is essentially trained on 18 billion tokens, 4.5 from PubMed and around 13.5 from Corpus, PMC. 18 billion tokens, and has been trained and fine-tuned on that specific data set, which makes it much more easier for us as users or as second generation developers to clone that, fine-tune it on more of a smaller subset of those papers and have our like constrained specific results. We have less established because Llama has lesser community support, which is quite obvious. Following this, we actually enter into BioBert. What is BioBert? How this thing works over here. Throughout the our presentation, like I failed to mention this one thing, that what's BERT actually? What does BERT stand for? So BERT actually stands for bidirectional encoder representation from transformers. And why bidirectional? That this term comes from its pre-training portions of BERT. When BERT pre-trains, there are actually two different ways of pre-training an LLM. It's either auto-regressive encoding or auto-regressive encoder or auto-encoder or auto-encoder language modeling. The two different types of language modeling for pre-training a transformer. BERT is the better one. It like reads a sentence both from left to right and right to left parallelly before performing any of its tasks, be it NER, named entity recognition, relationship extraction, dependency parsing, question answering, or even answering specific questions pertaining to the dataset that is fed on to the particular model. BioBert on my left has this entire pre-training. Like if I am allowed to zoom into it, PubMed has around 4.5 billion words. I want to make sure of this, that this is only the free version of PubMed that BioBert has been trained upon. PubMed, like I and Gyan sir were calculating the other day, PubMed has around 60,000 articles, and every article's around if every article contains even around like just a basic amount of 3,000 words, it exceeds a lot than 4.5 billion that's over here. So we came to the conclusion that BioBert was only trained on the free articles that are freely accessible to the user. That's the pre-training corpora. And if we can just zoom again into a little bit here, that's the weight initialization from these corpus. And again, we have our pre-trained BioBert with the biomedical corpora and fine-tuning over every specific task that we want. For example, if you want a particular gene-gene interaction, if you want a protein diseases interaction, or even if you want a gene-to-disease interaction, BERT can be fine-tuned on all of these datasets, provided we have a set of data that's not entirely different from biomedical, but can be used to fine-tune our entire model. Then we have fine-tuning and the entire. So essentially what we come to the conclusion is BioBert, a model fine-tuned for biomedical tasks, can perform tasks much better. What tasks it can perform? Like entity recognition, question answering, giving the relationships between any two genes. Yes, sir.
In this table, it shows the gene-disease relation.
Yep, sir.
What it mean? What is definition of gene-disease relation? Means in a sentence, a gene and disease mention their relation, or in a paragraph, like how it is done in the table in the bar.
I was just completing the architecture and just coming to this performance part that I had kept over here. So BioBert essentially outperforms the BERT that we have. It takes in around, it contains around 97% of BERT's initial parameters and weights at only around 60% of BERT's training computational training capacity. BioBert can be trained on distill BERT, another iteration of BERT that can be run on local systems as well. Over here, to answer Gyan's question, this table actually shows relationship extraction test results for the gene, disease, and the protein chemical. PRF, they represent precision, recall, and F1 scores respectively. Precision is again like if you remember the confusion matrix from our machine learning classes. So precision matrix, it's essentially the false true, the true positive divided by the true positive plus false positives.
The question I'm asking is that gene disease relation, when there is an input text is given.
Yes.
How it is defining that there's a gene disease relation exists or not? Is it a kind of just a binary information, gene disease relation, yes or no? Or is it a relation which is like a quantitative information? For example, there is a paragraph. That paragraph has multiple genes appearing. There are multiple diseases appearing. How the gene disease relation numbers will be calculated from that?
The second way, essentially. Like, for example, if there's this paragraph where there are multiple genes and they are then located with a particular disease, then that has been used for training and fine-tuning of BioBert. Now, when BioBert is given to analyze the relationships between any set of n genes and any set of n diseases, it is able to map those genes to those particular diseases as it learned from its during its training period. And these are the
Um,
specific scores for like precision recall and F1 for all of the information that it has been trained upon. For example,
but you
when
can
birds,
calculate, but you can calculate precision or recall when you know already the information what are true positive, false positive, or
yes,
true negative,
it
false
was a
negative.
validation data set.
How
It was
do
not a testing
yes,
data set.
but how the validation data set is created? How do you know whether this gene or disease related or not? What kind of data was used here?
I mean, still like that's okay. I guess I'm able to get your question. During any LLM model or during even any machine learning model, there are like two or three different types of data sets we have. One is the training data that we use to train our models over like entire corpus, the big 18 billion corpus that we have. The second one is our validation data that we use to test our accuracy of our models. And all
May
three
I
of these are
interrupt?
made by researchers.
Go ahead. Yeah,
So I think we're not talking about general training, like the general techniques or strategy we're using in the machine learning or deep learning model, but we are specifically talking about what is like the training site in this given data, in this given result. So like the training site, the cross-validation site, or like the test site. Okay, yeah.
Mm-hmm. I mean, I'm pretty sorry, but I couldn't get your question actually. Like, was it a question or like you were adding information?
Yeah, so I'm asking that what is the specific data resources? I mean, like how you divide these sites, like the training sites, the test sites, or the cross validation sites from their paper or something. So could you give us like a little introduction about this? How they did in their paper?
The standard 80-10-10 procedure. This
so
I'm sorry. This
so the
80% of the
question
data
is,
would be used.
yeah.
I mean,
So
throughout
what
their
was the
paper.
data?
Huh? I
So
get.
I think the question is that what data was used and what training and test they did, and like, do you have some information about that?
Absolutely. So they use the standard 80-10-10 procedure. I'll open this one as well for you.
8010. Okay. Yeah.
I'll open. I'm getting it, sir. I'm
So
opening it.
because 8010 is also five-fold cross validation, right? They can use. So they did that.
I'm showing you the exact Y as well of how every single data is there.
Right.
But to my knowledge, as long as much as I reviewed their code, they've opened. They have used standard cross validation parameters of 80-10-10. Like 80% of that entire corpus would be used for training,
Training.
followed by 10% of validation, and then again
Yeah. So
unknown
this like
10%
it
for.
will be a five-fold cross validation. They use 8010 and then they do it five different times. 8010.
Yep.
Am I right?
I'm actually locating this. If you can see over this.
You need to silent share that window. You are sharing this PowerPoint
Yeah,
window.
yeah, yes. Just I'm trying to zoom in over here before I share that.
So, Dave,
Is my
can
screen visible?
you? Yes.
This is the pre-training that has been done for particular corpus. And I'll over this, like I wasn't aware that I would be asked this question, else I would have added these results as well. I'm adding again the data that they had used.
So these are the BioBert which are trained on different corpus.
Yes,
So
sir.
Wiki, books, PMC, and PubMed. Okay, all of them. Okay, the table you are showing that ROC performance table. Okay, if you go to that performance table, the previous slide you were showing,
Mm-hmm.
and the
Sir,
slide.
I will just add one more picture over here to as well.
Okay.
If you can see this, the statistics of all the relations that have been extracted. Following
Yeah.
this, I'll add just one
Yes.
task.
So yeah. Yeah. So this is a biomedical relation extraction database, entity type and number of relations. So GAD is what the full form of GAD? Gene and Disease Association, maybe gene and disease.
Gene diseases. That's all.
So there are just 5,300. Where these relations coming from? Gene disease relation 5,300, and there are EU ADR. There are 355 only. Protein and chemical are different, but where this gene disease coming from and how they looks like, how they have been computed, they are like a real gene disease association, or is that they are like inferred gene disease association?
These are all real gene disease associations because since they have used these data sets as like they haven't computed these data sets in their paper. They have used these in order to validate their models, in order to pre-train and then work accordingly in their model.
Yes.
So like, let's say if I'm
So that's what I'm saying. So if they use these 5,330 gene disease pairs to validate their model, right? That's what you're saying. They use
absolutely,
these pair of gene and disease 5,330 to validate their model. My question is how much these 5,330 themselves are a real validation? Are they known gene disease association? How they looks like, how they have been inferred that this gene is associated with that disease, where that was found. Do you understand what I'm saying?
in another paper actually, like if I can actually source that paper, that I could actually share that if you would
Yeah.
like me to.
So there's
Well,
if you
share
give
that it was
previous
actually a
slide,
paper from 2018, Liam and Kong. They had
there,
formed this
no, there was
entire data set.
Bhushan and Nagarajan paper was there in the previous slide. If you go,
Yes, sir.
the slide you were just showing me with those precision recall numbers. Yeah. Just don't zoom out. Little zoom out. Little zoom out. Little zoom out. Not zoom in. Yes. Yes. So here it says the notes scores. So precision recall scores on each datasets are reported. The best scores are in bold. The scores on GAD and UADR were obtained from Bhushan and Natarajan 2018. So the scores on GAD, what is this about? This GAD, GAD? I
GAN
mean,
and G's and diseases data sets. That's just the
yes.
data set name.
Where is the data set? Is this data set accessible?
Yes, yes. I'm actually locating that itself. It should be accessible.
There should be somewhere it should be
Yes,
mentioned.
it's open sourced. It's open source. Just give me 1 minute. I'll just. How about I share it to you? Can I share it to you somewhere? Because I
Sure.
have this data on my fired computer actually. It was actually an
This
open source paper that came in 2018, according to what I'm reading right now. And I actually never went into the dataset building. I was pretty confident about.
so this is a data set which has around 5,000 pairs. Each pair
Yes,
is a gene and a disease. Is
yes,
that you're saying?
yes.
Okay.
And on the upper end, like these taskbars, if you can see these ones, these are the ones
Hmm.
that Bert was actually trained upon.
Yes.
When BioBert was trained on this, these were the accuracy on these data sets. When BioBert was trained on this, these were the accuracy. And over here, if you can see, the highest has been over here. That's the recall score actually. But the highest accuracy precision has been found over at 77.02 and 83.5. These have been the highest precision and recall scores.
So BioBert 1.0 and 1.1 is saying that what is the difference between 1.0 and 1.1? Because it's, I mean, 1.1 is just an addition of just PubMed, or it is like a so 1.0 is PubMed, PMC both. This is 1.0 says, and 1.1 says just PubMed. What does that mean?
It was the second iteration of the BioBert particular model. I mean, like the number of training steps of 1.0 was actually 270. Like BioBert, when it was released, it had 3 versions. One was the smaller version of around 17 million parameters, the BERT uncaged at around 110 million parameters, and the BERT large at around 17 billion parameters. Similarly, when BioBert came out, it had 3 training steps. The smaller one was 270,000, and for the bigger one, 470,000. When version 1.1 came, it had a training steps of 1 million such steps. Like I have that entire data right in front of me. Like even when we are the next slide that I'll be showing you, I'll show a small comparison between version 1.0 and 1.1. The only difference between them is the training steps over a particular data. 1.1 had a more accuracy of around like 4 to 7% compared to 1.0. 1.0 had around 32, while that had around 38 point something percentage. I'll show it right away. So version 1.0. This is
go ahead. Let's continue. Maybe things will clear later. Yeah.
So I'll just mention this one more thing. In version 1.0, right over here that we are seeing, like this one, PubMed had around 200,000 steps, and PMC had around 270,000 steps. When I'm talking steps, I'm talking about the training steps in order to build the model during the pre-training of the model. And this was the final version 1.0 at around 470,000 steps. When 1.1 came, it added more amount of PubMed, like the amount that wasn't completely free had some amount of private information from, not private, paid information from PubMed. It added those datasets as well and brought to 1 billion training steps, almost like more than double of what the final version of 1.0 had with itself. That was all about it. And other than this, like there wasn't any such specific update. But yeah, there was a massive results update that was noticed between version 1.0 and 1.1.
Okay. Let's continue. Yeah, let's continue. Yeah.
This is essentially like the previous one was actually biomedical relationship extraction between both gene diseases and protein chemicals from the ChemProot dataset from YCONG 2017 or 18 something. And one was Balabram and Natarajan dataset from 2018. Those had the gene and disease dataset, and this one is the question answering dataset results. That is, I give the model, I give BioBert a particular query, and it answers me specifically to the answer to my query. For example, like SLM, these are again strict, lenient, and mean reciprocal rank. Over here again, these are the results. And I guess I've made pretty clear, or I have delved quite deeper into why I have been preferring BioBert over other pre-trained LLMs, because it has the access to these fine-tuned datasets from Basubram and Natarajan, from ChemProot, and from the other question answering datasets as well. And its performance on all of these tasks, NER, RE, QA, it's better than even BERT, GPT-3, and even others. And also we can always fine tune this, which comes to the second half of my project completely. The graphs that we see over here is the one that you this is like right now one which you were talking is the difference between 1.0 and 1.1. And what happens if we increase the data set, the number of pre-training steps, the number pre-training size, and after fine tuning, how does this graph look like and how does it go like? This essentially shows the
What is this
variance.
BC2GF stand for?
BC2, a data set again, sir.
What is that data set? So NCBI disease data set is maybe all the diseases. What is this?
Yep.
This database is about?
It's a
BC4
biomedical
can be.
trained data set created again in 2008, and this was solely created to evaluate the performance of BioBert, and it stands for evaluating like every resource that I'm reading. It contains a set of sentences and their corresponding gene annotations. BC2GM.
Corresponding gene annotation sentences.
It contains a set of like that's what I'm reading. So.
Okay. And NCBI disease is just a diseases. So these are all just the text. These are just text, right?
When you mean text, I mean text, special characters, numbers, everything.
Yeah. This is just text. This is not like an Excel sheet of certain other information, the other data.
Excel sheet, like how do we generate Excel sheets?
No,
Excel sheets
no,
also
the
come
data.
from
No, the data is okay. It depends on what those number represents, like what the data represents, right? So this is just I would say this is just like a literature text. That's a one kind of data. There is another kind of data. It's just a list of PubMed IDs. There's 1, 2, 3, 4, 5, 6. That's the data, right? That's the number. That's the kind of list of numbers. So there is if I said there is a data, there is a database where you have just all the genes under their names, their chromosome positions. That's also a database. Or there is a database with which are just a list of all the proteins and which interact with other proteins. That is also a database, right? So database or these data, the question is what they represent, what they mean. So when you say these are, so these are kind of text sentences, right? They're just sentences by sentences they're put, or it is something different. It's a kind of a table of all the genes. Let's say NCBI disease. Okay. There is if it is a disease database, I expect it will be kind of like each row is a disease name and then the information about disease, or maybe some sort of disease identifier. So that's more like a dictionary of disease. I do not know, but I'm just curious to know like what this database represents. There, just like remember, like when you are showing me the Google Colab running those knowledge creating knowledge graph, the input were links, hyperlink for the Wikipedia pages. What those Wikipedia contents? Text. Those are text sentences, information, right? It is not a kind of a table of all the students record, not like that. This is what I mean. Because depending on what you're giving, then it makes sense. It's easy to understand like what kind of training you're feeding in to these models.
So do I open any of these datasets in front of you?
No worries. Yeah, that's fine. Yeah, we can always follow
because
up later.
I have like I just built it over here. If we can go back to here,
we can follow up. Okay. Yeah. So this is performance, if I'm not wrong.
Yes, this is the accuracy of the models on the training datasets and how each dataset performs. Providing along with this, I also wanted to add this file.
So, Yubo, are you familiar with these databases in your experience?
Yeah, I can't see clearly. I mean, I'm having some connection issues. I can't see the screen clearly. I'm asking how to take a screenshot for me actually.
Can you zoom? Dave, Bluetooth would zoom out. Yes. Then we can see the full table. Yeah.
Yeah. Okay. Yeah, it's loading for me. Okay. Actually, I went through this and these are
You
not,
know about this
this does
database,
not
right?
look very familiar for me.
Okay. NBCI disease, I thought it's a NCBI disease. It's a typo or is it me who's right? Can you go a little up? There was a, because NCBI disease mentioned other places as well. So because I think NBCI, it is again into NBCI. Can you go in the graph?
In the
Graph.
graph, okay.
There was a graph you're showing. Yeah. Let's see. So this
It's
is
the type.
NCBI. Yeah. So it's a NCBI disease. And they call it NBCI disease later on the table.
Um,
Okay.
I'm quite thinking it's a typo. I'm not quite.
It's a typo. Yeah. NCBI is a. I mean, to my knowledge, NCBI is a proper name, but NBCI is a different name.
So you just muted yourself.
Yeah. So NCBI is a National Center for Biomedical Information, but NBCI they might have their own name. Give me 1 second, Dave.
Hello.
So, okay, but this is something, yeah, this is not something important right now. Yeah, we can follow up on that thing. Let's see.
Like,
Yeah.
if you can allow me, I would share you this tab. Like, if you can see this,
Yes,
this,
I see that.
this actually contains much more. This is actually the source where all of these data are located. So why this data came into being and what is the origin of this data and how can we assure ourselves that this is the correct data. This is where it comes from. NER performance, the biomedical benchmark leaderboard, and finally their metrics, model name, model name, and how we compare everything.
Oh,
So would it be better
okay.
if I would share this link in the chat itself, and maybe everyone could just play around with these models
Yeah,
and
we
compare
can
them?
follow up on this one. This looks like it's a kind of a table or something. Results in paper with the code. Where you are getting, okay, the results are in the table here on the right side.
Yes, sir. No, it's kind of it's not a table. These are all changeable parameters for every model and every data set and every task. I can change these parameters
Okay.
and change the
Is
metrics,
it
find the
so?
and
Is it a kind of tool which is available to play with?
yes, yes,
Okay, it's online available, right? Can
absolutely.
okay, then we can follow up on this.
Do I send the link or attach it to the presentation or anything?
No need for now. Yeah, let's continue your presentation, and we can follow up on this thing. Yeah, these will be some like follow up for later. We can do that.
Okay. Give me 1 second. I'll share of my audience later. Perfect. So now that I have been able to make, I guess I've been able to convince everyone why I'll be going off with BioBert and not, why I'll be going off with BERT and not Llama, and under BERT, why BioBert, and how I'll be cloning that off from their online repository and making specific changes on it. Now comes an important part. Since BioBert, that the one that we are using, has around 18 billion, has been trained on more than 18 billion tokens and has a set of its own parameters. How do we clone that to our local system and then fine tune it according to our specific needs? For example, if I just want gene to gene interaction or gene and protein interaction, and their specific benchmark results on these data sets, how do I clone it and then like execute it in code? There comes a separate section called LoRa. LoRa stands for low rank adaptation, and is essentially a method. It's not a tool, it's not an algorithm, it's just a methodology wherein we attach a set of a blank set of parameters and a softmax function at the end of our cloned model. And when we have a small subset of very specific papers that we want our model to train on and give specific information out of those papers only, then we retrain our entire model and this empty layer, LoRa, on this specific dataset. Provided post this training procedure, the parameters and weights of LoRa get updated and at a much lesser computational and time cost, we are able to achieve a near same accuracy on all of these datasets as mentioned on the left hand of my screen. Like it reduces additional parameters needed for fine tuning up to by 90%. And parameter efficient transfer learning. It is kind of like a more house way or a more standard method of transfer learning, which maintains around 95 to 98% of fine tuning with just a fraction of parameters, like as discovered from this paper. Then also it outperforms your standard tasks by 10 to 15%, as mentioned again from this paper. I'll just zoom off into this graph once again. This is the Vigo dataset, again a dataset that contains, yeah, this contains again all of the genes, proteins, and diseases. The biomedical data, all of this combined, and accuracy here means of next sentence prediction, next word prediction. Prediction accuracy, this is the higher one. And this was this one question asked me. 0 to 1 is the normalized accuracy. 1 stands for 100%, that's the full final accuracy. And if you can see the lesser one, it's actually LoRa that almost achieved 90% accuracy than the actual models, which have been trained on immensely huge servers. We can actually use LoRa in order to bring this to our local laptops, achieve a higher accuracy, and quickly adapt BioBird and bring it to our tasks that we intend to develop. Like, did I make sense of them? Hello?
Yes, yes.
Perfect. So it improves model performance, efficient resource usage, and makes it perfect for medical AI applications. Now we head to the limitations. Addressing hallucinations, the biggest limitations of LLM is actually hallucinations. And why it happens? Because since LLMs have this intrinsic quality of predicting other data, of predicting like information, there are certain cases when they predict information that's absolutely wrong or absolutely untrue. And to save us from not believing those information, we have these two methods. One is by using either RAG pipelines, retrieval augmented generation, or RAG, retrieval augmented language model. Or the second hub is through using knowledge graphs and graph neural networks. I'll go off one by one into which one is better, how much it's better, and why it's better. The three questions: which, how, and why. The preventive measures, and I'll just in very short over here, it explains what RAG is. RAG is essentially cloning a model, giving it a certain set of data and asking it, you need to answer me questions only based on this data. This data becomes your Bible, and you need to answer and comprehend all of my questions only from this and your previous knowledge. You need to fine tune everything on this data only. This makes it adaptive for situations, but facts could evolve over time. And it's one of the best ways for generating reliable inputs. For RAG, again, there is this entire methodology called LangChain, wherein you have a set of prompts that are human-like, and you feed them all directly to the model, and then the model generates prompts based on the human index prompts that have been fed to it. So technically, the entire system works in this way. I have a set of human-like questions that I would feed into the model exactly at the beginning. And once it's fed, then the model would give in an output, and every time it gives an output, a prompt, then again the next index prompt of the user is again fed into the model, which continues its fine-tuning, until a complete system is established that employs RAG pipelines in order to provide more reliable outputs.
Mm-hmm.
May I have questions on this one? Post this, we will be going to our entire proposed model, what I propose, like what I've been talking about this entire time. Just post this slide, we will be going to that. The answer, any questions? Post it.
No, all set. Yeah, go ahead.
This one was addressing hallucinations using RAG pipelines. Now we come to this entire synergy between LLMs and knowledge graphs. Why knowledge graphs are important, and how we can build these using LLMs, how we can use these knowledge graphs to retrieve information that we want, and how proceedingly we would work. This entire flowchart shows all the possibilities, all the permutation and combinations that can occur between LLMs and knowledge graphs, right from KG enhanced LLM pre-training, LLM inference, interpretability, training objective, instruction tuning, and probing and analysis. Like if you can see over here, there are three segments, like three initial parent classifications, as I call it. When KGs, the knowledge graphs, enhance the power of LLMs. Second, when LLMs augment KGs, when LLMs are used to build these knowledge graphs, when LLMs retrieve information from these knowledge graphs, and thirdly, when both of these work in synergy, when both of these work together, synergies, knowledge representations, and synergized reasoning, that the fusions. So this becomes the entire.
So Dev, these different options, these are like different methods where there are already some work done, or it is just like ideas.
Uh, I I can't guarantee like that in all of these permutation and combination there has been work done, but these are all the possibilities. But in most of them, work has been done, and we can enhance the work that has been done using our proposition model.
Okay.
But definitely, yes. The next slide that I'll be proposing, the proposed model that we have developed over time that hasn't been worked upon by anyone. Like I tried my level best in order to search papers from Archive, Google Scholar, PubMed, and even from
Okay.
Papers with Code, but couldn't find out any model or any architecture that plans or maps out to the one that we will be proposing.
So here it says one of them is the KG enhanced LLMs. In that, the middle one is KG enhanced LLM inferences. In that one is the retrieval augmented knowledge fusion. Is it a RAG, regular RAG, or is it kind of a different thing?
Differently. And I guess the next question would be how and why it is different. In RAGs, we feed in input documents. In retrieval, in the one that you see over here, we feed in the prompts in the format of knowledge graphs. In just the next slide, I'll be showing of them as well. Like I have this entire corpus of papers that talk about LLMs and knowledge graphs, and over time I have come to this understanding.
Yeah.
So like was able to make that difference very specific, because in RAG you feed in prompts that are saved in the form of documents, and in this format RAKG you feed in prompts that are fed in the format of knowledge graphs.
Yes, I like that.
So,
yeah.
Then we move to this model. This, if you can see, everyone can see, this is just a pictorial representation of my whiteboard, and this actually is the model that we have been talking on. We have been like brainstormed into thinking with a lot of input from Gyansa. This finally comes into what we have up till now. What all of the literature that we have read up till now is essentially we parse in a query into an LLM, which then builds the knowledge graphs. What we saw right over here. Sorry. Sorry. Which we saw right over here, that how we build knowledge graphs using LLMs, how knowledge graphs help LLMs to retrieve information, and how both of them work together. Whatever corpus that has been in circulation up till now essentially believes in sending in queries, giving it to the LLMs, and building knowledge graphs effectively. What we propose is a two-stage architecture. The query would be passed on into a BioBERT plus LoRa model. Everything, whatever like have been talking up to now, the steps that I have built, I'm trying to like compose all of those into a composite structure, a composite architecture that we will be working on next. BioBERT that we will be cloning off from the internet, LoRa that we'll be using to fine tune all of our smaller subset of papers, and using all of those to build, to just generate a specific result and the citations of this query. For example, if the query is, what are the, like I was asked this query last time by Gyansa himself, what are the PDP symptoms of Parkinson's disease, and how do you get those gene regressive, those linkages? I was asked this question. What this model would do is it would give you the specific result if it's available online or if it has learned, along with the citations. where it feeds those information. It can be any scientific journal, it can be anything from PubMed, PMC, or it can also be from anything like any other scholarly article available online. It gives these citations, which is then fed to the second half. The second half is another LLM sitting right there, Distilbert or Llama, which I'll again come to while using these. And this model will then build these knowledge graphs. So we again come back to here. This one, LLM augmented KGs, LLM augmented KG generation, and this entire plethora of options of permutation and combinations. This will be the second half. Again, Again, if we come over here, so this one was one example that I had found on as how LLMs work in synergy with knowledge graphs. How LLMs can be used as agents for reasoning with GAs. Which country is Barack Obama from? It is passed on to here, and this is the graph available. This is the graph fed into the system already, and an LLM goes into here as the agent. The red lines that you see over here are the connections built by the LLM when it reads the query input. It goes all the way from Barack Obama to born in Honolulu, city of USA. This is the final result or the final node that comes off as output by the LLM from the graph. I want to very much emphasize on the words I'm using. By the LLM from the graph for any particular query. It's kind of like democracy by the people for it.
One third, Dave.
Sure, sir.
Can you go to show that figure again, the Barack Obama? So you're saying that reasoning on graph. So when that person asks question, he asks the question to the model, LLMs and KGs combined, like that's a set.
Yes.
Can you explain this figure again? There's the LLM agent, and then there's the knowledge graph.
And the question comes off, each token of the particular question or the query is passed on into the LLM. We read that entire architecture right now about how every single token is passed off into the encoder, then again goes to the decoder and comes out as an attention matrix. The important entities of this question is country and Barack Obama. It searches in the entire graph the position of Barack Obama and needs to find out the country that it belongs to. So it goes to the next.
Does it mean? Yeah. So that means that we need to have already pre-built knowledge graph to answer this question, right?
To answer this question, yes.
Okay.
This is
this
is the model itself. LLM plus KG.
Yeah, but the thing is that when you have the question, that the knowledge graph has to be there. The actual data in the form of the graph should be there in the database.
That's essentially what we are building over here.
Okay.
Throughout the architecture that I just explained, that we'll be using BioBert, LoRa, then giving it to Distilbert, Llama.
Yeah.
We are building this KGs right away. And then this KG will be used in this BioWeek.
Okay. Now, in this case, what is this LLM? The yellow color, you say LLM agent. What is this one? Which LLM you're talking about? Because you always take the name, right? One particular
Absolutely.
LLM.
I'm really happy you asked this question. Over here, my personal idea was to use either BioBert or Distilbert. In this case, because of a set of reasons, again, that I'll be proving again in the next couple of slides, why I'm using these slides. But again, I'm open to experimentation as to which LLM performs better. Because Distilbert is just a smaller scale Bert. Bert, the bigger, the massive dinosaur. Bert is like the dinosaur in the room, and Distilbert is just like a reptile with all the scaring abilities of the dinosaur. I don't know all the technology.
Okay.
So that is why I'll be using Distilbert or BioBert for this case. But again, I'm still open to understanding from this entire pipeline as to which LLM would perform better according to previous research data, according to previous literature, which has a better possibility of working.
So Yeah.
Yes.
This is something is a kind of some publication. This LLM, these figures, this and the previous figure. Is it some sort of literature you are reading, or did you just made it? I don't think that you made it, right? It's some literature from online, right? Where you can read something about it. Basically, LLM and graph.
The second one, Barack Obama, was like one I had made, and the first one, this one, was literature. This
Even
is
the
literature.
previous slide, this one, yeah.
It's
So
literature.
yes. So yeah, I would like to. This is more like a brainstorming ideas because here it provide many different ways how the LLMs and knowledge graph could be put together. Yeah, because the things which we like discuss is just one of the way, right? There could be many different ways which could be more effective and they might have pros and cons. Yeah, so this will be something worth have more brainstorming in future. Yeah, but let's continue. Carry
It's
on
kind
what
of
you are
like,
saying.
even if you can just count all of the possibilities in here, you can actually merge any of the ways of using KG enhance and with any of the one with LLM augmented, then finally synergize it. There could
Yeah.
be an n number of ways by which this entire architecture could work, and we could never finally reach to the one that's best for us. But it's kind of like continuous R&D. So every single time we just
Yes.
need to keep in mind we are improving our accuracy results, we are improving our F1 scores so that we get to
Yeah.
a better stage. If you can just
Yes.
open on this smaller part, stage 1, stage 2, and stage 3. Stage 1 is
Yeah.
building those knowledge graphs and using those knowledge graphs to retrieve the specific information that we need. Stage 2 is combining them into a single multimodal agent that has an LLM as an agent and an information as a knowledge graph. And stage 3 is now uploading all of these into Neo4j. That again comes to a separate topic in itself. How I would combine Neo4j and multimodality in order to like portray that information to the scientist or the user who is using it. These are three
Yes.
different
Yeah.
milestones of unifying
Yes.
these two
Yeah.
blocks.
Yeah. Sure. Sure.
If we go to the stage 1 of our proposed model, stage 1 was essentially we given a query to BioBert. We pre-train BioBert with our LoRa. We feed in a specific
Where is your mouse? I cannot see what you are hovering. Can you hold your mouse? Yeah. So stage
BioBert.
1 is BioBert plus LoRa for query processing.
Yeah.
Okay.
LoRa enhances this by fine-tuning it for a very specific task. What it does, it inputs a biomedical query to the model, and this model then finally gives you the entire set of citations, the entire set of results as output. And this is a system architecture as defined as this paper itself.
Okay.
And this is the entire flowchart that shows how things work.
Okay.
Over here, we find the query processing system.
This flowchart where it starts. This flowchart is a little confusing. Where we start?
The data
Yes,
set,
yes.
as Jose just mentioned to me about how we will be differentiating into training set and testing set. It
And
goes
this
off
data
from
set is about what? This is the data set of what?
biomedical textual literature.
Oh, it's just like it's just a PubMed like corpus, you mean?
Yes.
Okay. And then you put the
You
split
can
it out.
always use a different data set instead of this. You can always, like, considering you have an Excel, you have an Excel data, or you have a different kind of like database of considering gene to gene interaction or protein to gene interaction. You can always like substitute this data set with your specific one. And I would still assure you that this entire architecture works for that as well. So this is then distributed into two sets, training and testing. Training goes into here, fine tuning and keyword extraction.
Hold on. The training goes to two different places: fine tune and keyword extraction, and then from the keyword. This and what is the goal of this here? This workflow, test results.
Fine tune BioBert over a specific subset of our literature to produce a higher accuracy and specific results that we need.
Okay. So okay, so correct me if I'm my understanding, but then why it is in training and test? Okay, so pre-trained by a bird, and it so I see the pre-trained by a bird. So training set the data fed into combined with the pre-trained by a bird. Am I right? And then you call them extension. I think that we are using the word BioBird V2 or BioBird plus LoRa. Is
Exactly.
that I'm okay?
Yep, exactly.
And then pretend what is KW BioBird then? Keyboard BioBird. Okay. Then and then fine tune goes to tune BioBird. Can you explain slowly? Okay, I'm taking this thing from a simple way. Okay, let's say our data set is corpus. Let's say from the corpus, I give you 100 different papers. Okay, that means the corpus of like the whole text of 100 different papers. That is going to training set. Then what happened from this 100 corpus?
80 comes here, 20 goes here.
Yeah, so let's say training. Yeah, so 80 comes here. 80 there are 80 papers are here. Then what happened to the 80 papers? Yeah.
It is distributed into 3 segments, like almost around 40, 30, and 10.
So 40 papers will go in the okay. So all those 80 papers go to 3 different, or it is like a 40 papers in keyword, 10 papers in fine tune, and rest of the paper in other fine tune. Is that you are saying, or is it all the going?
See, if you can just notice over here, all of these are essentially till the end again being fine tuned. After we have pre-trained like keyword BioBird, every of these papers is again being fine tuned. So essentially, it doesn't matter to which pipeline any of those 80 papers go. Everyone will be fine tuned till the end, and then again fed.
Yes.
Like fine tuning essentially.
But the thing is that it goes differently, right? These goes to fine tune there, but they go like, for example, let's say I have 80 papers in training set. 10 paper goes directly to fine tune. 20 paper goes to this BioBird fine tune, and then rest of the let's say 50 paper that goes to a keyword extraction fine tune. Now the result outcome with this will be different than if I have like a 40 papers go to fine tune directly, and then just 20 papers in BioBird and 20 paper in keyword, right? The results might be different. No,
I'm pretty sure that the result is never affected like that way, because what we are trying to understand is like how we are like choosing randomly papers and going into separate segments. This could also be an architecture where like all of the 80 papers go through all of the 3 pipelines.
Okay, yeah, this is what. So all the 80 papers, yeah, this is what. So can you explain me what these 3 different routes are to fine tune? What they mean? Why they are 3 different? Why not just one? What they're like? What make them different?
Perfect. We have our pre-trained BioBird over here. That's essentially just cloned from the internet. All the 80 papers they come over here. Our pre-trained BioBird gets fine-tuned over here to form tuned BioBird. Okay. All of the 80 papers then again come here, and BioBird is used for extracting the keywords from those 80 papers, the tuned BioBird. Okay.
Okay, and when you said the keyword extraction, so that from the tuned BioBird, it will do the keyword extraction. I'm slightly confused. Okay. Just okay. Yeah. Okay. You can explaining me that last question. Yeah. Let's see if it's clear to me. Go ahead.
Once keywords have been extracted, these are again like expanded into the final keyword set. Like we already have a set of seed keywords. Then this is merged with the keywords that are being extracted by the tuned BioBird over this entire set of training papers. And once this final keyword set is performed, it again comes over here. Now, again over here, pre-trained BioBird, there is this small extension added. This extension is of LoRa over here. Tokenize process the input query using the fine-tuned BioBird plus LoRa model. It's added and again brought over here. And this entire set of 80 papers is again brought over here. All these extended set of keywords, the extension of BioBird with LoRa, and the entire set of training papers is then utilized for fine-tuning. And we finally have a tuned keyword BioBird, which is then used for testing with the starting with like the 20 papers that we had kept aloof from everything, and finally we get the test results.
Like is this model okay? Is this the proposed model somewhere working or no? Can we see a kind of an instance like how this works? Like is there somewhere?
About the code, yes, you can see. But if you're talking about the output, I'm sorry, so that hasn't been
No, no.
completely
If the
envisioned.
code is there, yeah, if the code is there, can we just like say kind of a hello world program?
Sure.
Can I see how it works? This whole thing is working. Is there any way you can show it?
Absolutely, sir. I just need to share my tab.
Okay. This workflow is a part of any literature, or it is you made this workflow?
Kind of both, sir. Like it
No,
is
no.
there in some literature, and I prepared some of it myself.
No.
So
This workflow, is it a kind of
only
you?
the workflow, yes, it's there in literature, but the extension, if I were to talk about this extension, it's not there.
Where is your mouse? Okay. Yeah. Okay, I get to see
This
that.
is not there in any workflow, any literature. This is there in like
Okay.
I prepared this part, but the existing this entire workflow you can find it in literature. I'll attach all of those papers as well. These are only the links.
Okay. So you are showing something, right? You're going to show something. Yeah. Okay.
Is there?
Yes. So let's say so this is the so yeah. Can you explain a little bit about that?
Sure. Loading in the untrained BioBert version 1.1, 1 million tokens, loading it from pre-trained. Now defining the LoRa layer for self-attention mechanism. What it does, adds the extra layer of null features. That sends an extra empty layer that will be fine-tuned according to the
Give me
specific
1
subset
second.
of corpus that we will be giving it. Now this function, apply LoRa to self-attention. This is like if it is an instance and it just adds the LoRa layer to our pre-existing BioBert that we have over here, 1.1. It adds the LoRa layer over here. It adds the LoRa layer over here and to get self-attention right here. The dataset loads this squad V2 dataset, and I've just used an example biomedical dataset, and this again pre-processes all of that as well. I have this entirely. Once this is pre-processed, if you can see over here, this is BioBert tokenizer that we saw over here. This part. Is the architecture and the code making sense? Like just even the slightest? The BioBert tokenizer is being used for extracting the keywords. If you can see over here. For this loaded dataset, the tokenizer takes in the examples only second and returns the keywords of the the training set of the data. It goes all the way up to here. And this is the fine tuning, like BioBert plus LoRa, updating the parameters of the last softmax layer function in order to have that entire composite, this architecture, this place, like to reach here. To reach here, this is the part of trainer, and this is the part of tuner of BioBert.
Oh.
How about I show it to you, like both in one screen? I guess that would be better.
I can adjust that. That's fine.
Is it fine that I won't do that?
Yeah. No worry. I know it will be tricky for you, so yeah, no worry about that.
30-second task. I can do it.
So in the code, yeah, in the code,
Yep, ready?
Yeah.
This one was one I was talking of when BioBert tokenizer tokenizes all of this information from this data. This is here.
So yeah, can you? Okay, I think that this is something I would like to dig further. Maybe not today. That when you, because you're right now loading some data, so how this data looks like, what is this thing? Is it a
That's an example data set.
efficient?
Like I want to make sure that's just an example biomedical
Yes,
question answering data set. We
yes,
need
yes,
to
yes,
feed in our specific data set that we want. And that would essentially
yeah,
come from a subset of PubMed PMC anywhere.
yes, yeah. So yeah, so do you think that this code could be usable if we have a different set of data which we want to put to training?
Absolutely, sir. I'm still debugging this
Mhm.
actually this entire procedure. This is actually throwing me a small error over here. Like in the
Okay.
standard training arguments error. That's something that
Yeah.
I can debug and make it, I can fix
Yes.
it.
Yes. Yes.
Once
Definitely.
that's
Yeah.
like this architecture is almost ready. One
Yeah.
wherein we use training arguments, this part,
Yeah.
pre-training BioBert and then adding the LoRa layer. If you can
Yeah.
see, use the BioBert model, training dataset, validation dataset, and we have a very specific parameters as well that I'll show you to in the stage 2 of this proposed model. What are the
Okay.
hyperparameters that I will be using in order to build every single step? What will be the learning rate, the batch size, the number of epochs, the number of
Yeah.
per device training batch, and even
Okay.
the decay, the gradient descent weight. So I'll be showing
Yeah.
everything of this. Once that's done, it just generates responses. And this was one example usage.
Yeah.
One where
Okay. Yes. Yeah.
is my so I just wanted to ask this one question: is my architecture and my code making synergy? Like,
Yes. And this is
do
where
I
I think that I would like to have more discussion on this thing. I mean,
sure?
slowly, I'm getting. Yeah. Um, so, I mean, I would like to follow more on this thing. Yeah. So, why don't you continue? You're showing stage one now. Let's
Absolutely.
see stage two, right?
Okay. 1 second, please.
So, the stage one will be, I think that in this workflow, I get little not clear because in a stage one, you create the knowledge graph, right? The first thing is that,
No, sir.
no, it is
Stage
a
one
test.
is creating the specific text. Stage two is creating knowledge graphs.
Okay,
That's
yeah.
again.
So can you, okay, okay. So in your board, the whiteboard cartoon, you show that thing, right? Can you show your whiteboard cartoon that how it is connected to the bigger picture? Stage one, you get the text results, a proper text result.
This is stage one.
Okay, specific results. Okay. So when you ask query, for a query, it goes to the model which is trained with the Biobird plus LoRa. It gives a specific results, right? Plus
Yes, sir.
citation. That's the stage one. Okay, one question here that let's say if I'm asking my query and LoRa is a pre-trained, right? So that means those 100 papers which I give citation, let's say 80 citations, no, not citation, 80, um, no, what I'm saying that how you decide what is LoRa here for different question. What I mean that let's say my question is coming that, okay, what is the role of T53 in cancer? That means my specific fine tuning articles are only those cancer papers, or maybe fine tune article could be some additional subgraph, like a subgraph of data. So I'm using the subgraph as a kind of another data which we have, let's say. Um, then do you think that if I provide you that, would it help? Yeah, hello.
Yes, sir.
So what I'm trying to understand the LoRa part.
I,
It is
the amount that I am getting is like you want to ask like what if the background of query changes? For example, if I have a query like what is the role of TP53 in cancer, and my second query comes out, what is the symptoms of Parkinson's disease, or what is the gene-to-gene
yes.
interaction?
So yeah. So do you think that they should have a different LoRa component there?
You can increase your LoRa component. You can increase your LoRa component to all the data that you want to ask. If you feed it with, at the same time, you feed it with both cancer data sets as well as Parkinson's data sets, then it becomes much more ready and efficient to answer both its answers, both its questions.
The only thing is that when we and okay, and okay, this is something. Yeah, we need to dive into this part. Okay, let's yeah, let's think like let's say with this. Let's say assume it's working. Yeah. Okay.
This is stage one, and finally stage two. Stage two was what we had kept over here: Distilbert or Llama and KGs. I will request for a second, please. Sorry. Stage two. The square off between. Are you not seeing the complete screen? Why is it coming this way?
You had to little zoom out because you
Is it
cut the
better?
on. Yeah, but you see the little bit of on the right side boundary you cut. If you zoom out a little bit,
No, sir,
we
nothing
can
is
read the
being cut.
full.
Like this is the
Okay.
full thing.
Okay, got it. Okay, that's fine.
So like actually I had much content to put in one slide now, so things appear as if they are
Oh,
grading,
no
but
problem.
actually
No
they are
problem. Yeah, go ahead. Yeah, go ahead. Yeah, let's see.
So this is this one question between Distilbert and Llama. And what's Distilbert? Distilbert is just a smaller Chinese version of BERT, like not essentially developed by China. I'm sorry, but it's kind of a smaller, faster, cheaper that can run on your local machines, almost good as your BERT itself. It retains 97% of BERT's understanding and runs at 60% faster. Essentially the trade-off between BERT and any like local of this. Sorry, I just had a blackout. Sorry. And the second part comes of Llama. Llama, known for its large-scale capabilities, handling complex queries, and generating knowledge graphs. Which one to use? Why to use? To create these knowledge graphs.
Hello, Dave, are you still there?
I'm so sorry, sir. I had a network error. Like I just
Yeah.
got disconnected.
Okay. Okay. Go ahead.
It's I'm sorry, I just need to restart a second. Distilbert and Llama. Distilbert contains around 97% of BERT's understanding, being 60% faster, much better to that of BERT because we can run it on our local systems. It's more powerful and it's cheaper and faster, and we can actually afford it. But Llama, it's one that's used for large-scale capabilities, for handling complex queries, and like a much greater scale. The second one that we have is the systems architecture of processing BioBird outputs. The second step of this stage two, if I'm able to make sense, it takes output from fine-tuned BioBird plus LoRa model, and this is then fed into the distilled bird or llama. That is, we take in the output given by the previous model and feed it into this newer model. Following this, we create the knowledge graphs, the nodes, edges, and entities. That is, we always have these three steps in order to create the knowledge graphs. First, we have the named entity recognition in order to recognize the nodes of the particular graph. Then we have the dependency parsing or the relationship extraction between the nodes so that we understand how any two nodes in that particular graph are related between each other. And third, we have the like displaying them or building those graphs, attaching weights to those like edges right over here. Like if we have these medical knowledge graph, if I would just zoom, like, am I visible?
Yeah, I can see that. Yeah. So even if you keep it smaller, it is readable. At least to me, it is readable. So it's fine. Yeah.
So Hausu sir and Yubo sir, are you still there?
Yeah, I'm still here.
This is
Okay, go ahead. Yeah.
how each one is being used. KG enhanced LLMs, LLM augmented KGs, and the authentic synergy that works
Oh,
in
okay.
between.
This is funny thing is that the graph which you're showing is
Yeah.
coming from some literature, right? Because it is a Parkinson disease graph. I can see it
Yes,
came
sir.
from Parkinson,
Yep.
right? Is it some paper which
Yes,
actually
sir.
tried to address Parkinson?
Yes, yes.
Yes,
I believe.
actually, this is very good. So I tell you that in a tool like this in the future, this is what I want here. Do you see? Do you know what is pink one here?
It's a gene, I guess, that causes
Yes,
Parkinson's disease.
yes, yes. Now it recognized pink one here, which is fine. But then it had motor neurons. I mean, okay, I'll not go into detail. But the thing is that this is what I want. This knowledge graph should be able to identify the right entities before putting them into the graph, right? Otherwise, the graph will be too crowded. A lot of things will be just redundant from the like a usable perspective. So let's say, for example, here in this medical knowledge graph, for me, I'm more interested to see, okay, pink one causes Parkinson's disease, also could be a disorder, but I know motor symptoms. Actually, tremor is a part of motor, like should be connected there. Anxiety is not required for me. Language underdevelopment not required for me. Pervasive development disorder not required for me. You see here? These are all could be the nodes in the knowledge graph, if I'm not wrong. But
Yes.
like 50% or 60% of them are useful for me, and under for like a redundant. They're not useful. I'm not saying they're noise or they're wrong. It's just that they're not relevant.
This relevancy, I guess, needs to improve through multiple iterations.
Yes, and this is where we add a one more layer on top of knowledge graph. When you have visualization, I'll tell you that it is okay that we have the full knowledge graph. Let's say it's like a full dictionary. We have the full right. But what we are looking at is just the content of a piece of that in visualization, right? Because when we start analyzing the data, we want the purpose of visualization is to further get the insight from the data by superimposing some other data. So I think that, yeah, let me not divert you from the main your idea here. Let's go and then we'll follow up on this one. Yeah, go ahead.
Sure. Generating knowledge graphs and then finally using it for visualization by giving it to NetworkX or Jeffy or uploading them.
So step one, I think that this is what you're saying, right? Is step 1, 2, and 3 and 4, right? These are
yes,
4 steps there. Okay.
The 4 steps in stage 2.
So system architecture, process bypass output from the fine tune. The left figure. Can you explain a little bit of left figure? Generate knowledge.
Or the upper one?
Upper one. Both. I mean, just explain that what. Yeah. So what I'm trying to say that when you put the figure, explain me what is your purpose for the figure. What do you want to say from this figure?
Absolutely. If we can check over here again in this flow chart, there were 3 segments. One was using KGs to retrieve information, using LLMs to retrieve information from knowledge graphs, using LLMs to build knowledge graphs, and finally when both of them work in synergy. Over here, when we come over here, this is essentially what these 3 are. One is using textual input. KGs give structural fact, domain-specific knowledge, symbolic reasoning to the LLMs, and the LLM act as the agent to find out, to retrieve information from the KG specific information and give that as output. The second one, KG related tasks. When we ask the LLM to build a KG, it takes it gives general knowledge, language processing, generalizability to build this KG and gives that output. And when these two combine, it becomes a synergy.
Okay. And one example is that, let's say I have a full knowledge graph data built by a knowledge graph.
Knowledge graph.
Yeah. So that means that we have this knowledge graph, which we do not know how it is prepared. Let's say another group, or we are working with another company who already built a knowledge graph, biomedical knowledge graph. That means we have the data. Okay. Now we want to utilize this knowledge graph. How would you utilize here? You know what I'm saying?
Yeah, absolutely.
So
this is how we would use.
The knowledge graph is there.
Just the example that I just gave about Barack Obama and where he was born. We feed in the knowledge graph of Barack Obama, his entire database into the LLM, and the LLM acts as the agent. It goes off into like deciphering every single node, finding its correct path, and gives the final output by retrieving information from the knowledge graph. This is essentially KG enhanced LLM's architecture. Like only difference being that I gave the example of Barack Obama was a common sense question answer, and the one that we'll be using will be essentially med QA question answers.
Okay. So remember that I can provide you the knowledge graph data. Let's say the full knowledge graph data, which is even more trained on much more data. You're right now talking about just medical literature, right? The other biomedical knowledge graph data is actually even also trained on different databases along with the corpus. Many things.
Our project completely.
No, but it's finally it's a knowledge graph. So, but that knowledge graph is trained on a huge amount of data, which we can go into further detail. But I think that in a kind of an outcome of that you have a knowledge graph exact data, knowledge graph. Remember? So now how can we build on top of the knowledge graph to like a smaller size network and asking the questions? So remember that we have that thing actually.
How about I show you this next slide if it becomes a little better? If you can see this left section, this is essentially the entire architecture that we want to develop. This is what each section brings into the synergy. LLMs bring general knowledge, language processing, and generalizability. And knowledge graphs bring explicit knowledge, domain specific, and the specific interpretations that we want. Building all of these are from this structural facts, be it in the form of databases or Excel sheets, text corpus, be it from PubMed, PMC, and all of the online available text, images and videos, not for us. It goes into here and goes through all of this. Prompt engineering, like for a fine-tuning procedure, prompt engineering, graph neural networks, using Neo4j and GNNs in order to specifically retrieve information that we've also can, like this is again a loud thinking of my mind, we can also deploy feedback mechanisms in order to understand that every particular answer that's generated at each step is correct factually or not, by comparing it with information online as well as with information like that was fed to the LLM in the beginning. That comes over here, representation learning and few-shot learning. Few-shot learning is essentially a very like a very R&D specific topic of meta learning. Meta learning, like it comes from few-shot learning comes from there, which essentially means that we would train our model on very small amount of data, and then ask our model to give its testing on a larger amount. That's essentially the opposite that we do in classical machine learning. We train it on a larger data and test it on a smaller. We do the opposite. And apparently, according to some algorithmic tunings, few-shot learning has a higher accuracy than the classical machine learning algorithms in very small and discrete topics, of course, but there are such literature available. And then we can apply all of these to either a BAI-KJ that you had shown me the last day, biomedical instructor knowledge graphs, or even a recommender system or anything accordingly. And these are the hyperparameters for this stage 2, KG embedding and KG completion.
Okay.
Did I make sense over here?
Yes. Yeah.
Yeah. Actually, I just have a quick question, if you don't mind. Yeah. I was just curious, how would you plan to, like, you were talking about using large language model as an agent to query your knowledge graph, right? Yeah, I was just curious, how do you plan to implement this process? Because as far as I know, there are like multiple ways to like using a large language model as an agent to like do something. I was just curious, how do you plan to use large language model to query the knowledge graph or enhance the response?
Do I share off my code for that as well?
Yeah, if you have the code.
You can show that. First, you can explain, then you can show the code.
Sure. I actually have, the code that I would show for that person about, for that percent of using the LLM as an agent, it's in a very vague format. Like I haven't completely brought it in a solidified format, but this can definitely be used and it has been proven because the image that you're seeing on my left is actually taken from a journal. It's a literature journal that I was during my research, like I found it, and they have mentioned their papers as well. They've mentioned
we totally understand that it's a doable project or doable way or doable strategy, but we probably want to see how you implement those things, but not the general talk about those things. Okay. How you plan to implement those things?
Yeah. So I think that this will be. Is it your last slide, Dave?
I have another.
Yeah. So I think that Jose, what the goal was today, that Dave recently actually just proposed the idea I want to do internship. So I asked him to put a proposal, and once you see that this is interesting, then we can actually ask him to further go on implementation part. So I think that what we can do, that maybe we can give some like already questions they've got from us, and then he can follow up on that and come up next time to give a more detailed about the methods and the implementation part. What do you think, Roger?
It sounds good to me. I'm not sure how do you think?
Is House there?
Yeah, I'm here. So what I'm thinking is this is like a very good interview or introduction for the large language models and like the methods in those things. But I mean, this might be too general. I mean, too in the general level of the discussion. And for the citations or like the paper or the experiments mentioned in the slides, I think it's a little bit old.
Yes.
So to my knowledge, there are since the GPT-4 or GPT-4 has achieved a very high level of performance with the RAG strategy and about like embedding the query and the information together to as a like a prompt. Those kind of strategy has been, I think, very well used in the in a very large domain like the industrial stuffs. So I can show some example of that.
But do you think? But I think they are not free, right?
Actually, this is only about strategy. We could use some open source model to do the similar thing, I think.
Yeah, I'm trying to do something.
To have like something like a hardware requirement or the software requirement. So, I mean, this is like a doable strategy of doing those things. Like we could use that strategy to build an application. So I think this is applied level of the like to the final goal is to build an application to do some very specific work or specific task.
Yes.
Am I right?
Yes. We want to build a specific applications which could actually we can interact more like ChatGPT, but it will be more focused on biomedical research, as well as it will have a provide like a knowledge graph type
Yeah,
visualization.
so I've just Googled, like using Google Scholar to do some very basic literature research, and it seems that we could use, yeah, they are mostly using something similar to the modern or little more modern model like the Llama or the GPT to do the similar sign. For example, for the gene and disease, um, like affiliation problems. I
Would you
think
like to share your screen? How's you want to share your
I'm
screen?
just do very basic. I mean,
Mhm.
Google search for all those things. So it is okay to do so, but yeah, let me take a look again. Hmm. Yeah, and I think they are doing something for several different tasks. So let me take a look of those signs.
So, Jose, would you like maybe next meeting you can just share with us a little bit what you're doing and what you think about could be the right way to do?
Okay, sure, definitely.
Yeah. So then we can think about like how we can actually change, how we can work together on this.
Yeah. Just because based on what I researched in the recent, in the recent 2 years, like 2023 and 2024, those papers, I found that a large amount of using like the prompt um, to design a very specific and prompt to do the similar stuff,
Yeah,
like to
that's
find the
interesting.
connections between the gene and the disease. So that's yeah. So that's why I'm thinking that the literature review we've done in the slide might be a little outdated. I think.
Maybe, yeah, definitely.
Yeah.
I
Yeah, since we are waiting, I also want to talk about when I have some questions
sure.
about stage one. I feel like we are kind of overcomplicated the process. Because in my understanding, please correct me if I'm wrong. In stage one, we are only trying to find keywords from the query, right? We are fine tuning all those things. Yeah, and I think your current strategy was to fine tune Firebird or some variant of Firebird to identify the keywords. And yeah, that is a good way actually. Yeah, you will want to do it in the long run. That might be unavoidable. But for now, I think since we don't have a very strong data set of keywords, like ground truth keywords, like we don't I don't think we have data set of queries and the keywords in the queries. So I don't think we have uh, it might be too time consuming to fine tune the Firebird either. And I also think, in my understanding, LoRa is only suitable for fine tune very big models. And Firebird, in my understanding, is not that big. We can totally just fine tune it either on Google Cloud, either on cloud on our local machine uh, very easily. And if we can fine tune the full model, I don't think we need to use LoRa since the upper bound of fine tune with LoRa is full model fine tuning, right? Um, I think to identify keyword, the easiest way is just we ask a large language model to find the keywords for us. We just write a prompt, say we ask Llama 3, please find the keywords in these queries, and I think Llama 3 will help us to find most of the queries, most of the keywords in the queries. What do you think?
So one question, Ipo, that is this Llama, we could develop an application without paying anything?
Yeah, I think Llama 3 so far is open source, and I'm not sure we can do it like for commercial, but at least for research, we can. I think we can do anything we want. We have a lot of admins that are like either fine tuning it or just use it for their applications.
Like
So
show you a result actually.
what is
This entire like one that you said about we can actually extract keywords from biomedical data and
Yeah.
how we can create knowledge graphs. I would just take a moment to just show you a code and its associated result that actually even during my presentation, like I had mentioned about this trade-off between bird and llama, bird versus llama, and why I finally chose bird instead of llama. And I would like to show you a small code excerpt and also the code output, as in why we had to resort to this entire complicated architecture of fine-tuning BioBird and not just giving it to maybe just a ChatGPT prompt to find out the nodes and weights. How about I share my entire window and there I hope I'll be able to show.
I'm going to share this.
If you can see over here, this was actually a text that Janser had given to me. And this is actually a biomedical text. If we, I will just zoom over here, the model that I'm using over here is bird-based uncase, absolutely no fine tuning done. And if you could just ask me, I could just replace this with llama right away as well. Like I would just require around like 5 minutes to just change it into llama because all of the other properties remain the same. What it does is it takes in a biomedical text completely on multiple neurodegenerative diseases, including Alzheimer's disease, forms microtubule associated
so
protein.
this is
Now,
actually an abstract from a
an
publication.
abstract from a publication. Now,
Yeah.
like I just want to focus on what are the actual nodes, mutations in MAPT gene. That is, how about I share this doc as well? That would show you.
Yeah, so I'm thinking that the easiest way is trying to put the whole sentence into chat, something like ChatGPT or Llama to get the keywords extracted.
Yeah,
And you
exactly.
could cite how many keywords you could get from the large language model. Yeah.
And so I want to show you exactly why it will not work. Like
Yeah.
so this absolutely an idea. So we have the when we started our entire process, we started by giving it ChatGPT or
I don't
any.
think this is. I mean, I don't think it cannot be worked on large language model as ChatGPT or something. Yeah.
So I'm
I
trying
think
to show
it definitely could be. Yeah, so I can get the input text with the keyword extracted from the large language model. Yeah, they know the domain knowledge of those things.
this is the input text.
Yeah, could you
Okay.
put it in the chat? I will generate the extracted keywords. Yeah.
Okay.
This
Why
is
don't
the
you just copy paste this
Yeah,
into
send
the
it
chat
into
window?
chat.
into
Yeah.
what?
So can
Okay.
you put this copy this text into chat window so you the Hauser can actually use this and just to run it on Llama and see LLM
I
that
mean,
whether
yeah,
they
I
get the
mean,
keyword.
so I have a ChatGPT open, so yeah, but not Llama
Let's,
currently. Yeah,
yeah.
Sure.
Let's see. Yeah.
yeah. Let's take a look.
So you take a look on that, and I'll bring you what the output of any pre-trained model gives in. I'll
Okay.
go up to here.
Let me make a copy of those
This is the
slides.
text. It encodes this particular text, takes the last hidden text, take these nodes, edges. Once these are given, it creates a data frame, nodes embeddings and edges weights, which finally creates the graph. I want to actually show you this graph itself.
Um, So Jose, did you get the text?
Yeah, so I'm working on writing a prompt to get those things. Yeah.
This is the graph that this particular text will generate. And if you can see over this graph, since it has been built by BERT, so every single node actually has a 768 dimension vector attached to it, where it contains all of the information. Over here, sir, if you remember, around 30% of these, all of the nodes created were only valid. So these are the nodes that
The
you
nodes.
gave in.
What did you say? What are the nodes created by?
Sir, Hauser sir has also sent you in the chat the nodes, and you can actually compare those nodes with the nodes that I'm showing on the screen.
Yeah.
And among
So,
those, if you
okay.
could just
So, just one second.
compare
So,
and let me know
how's it?
how many are
You
correct.
correct me if I'm wrong, Jose. So you actually cut and paste here the nodes which are created from LLM model, right?
Yeah, from ChatGPT directly. So I'm using the untuned, just a very general version of ChatGPT to generate such keywords extracted from the given text.
Okay, keywords. So if I'm not wrong, they're almost same.
So
Am I
like
right?
it's on your screen, whatever you can see. And I
Uh,
just want you to again check which and
Well,
how many are correct. Because if
yes.
so using a
So
ChatGPT works to extract the nodes, it makes our works a million times easier. We
say
can
again.
directly use the API key and directly extract the nodes and then finally build these graphs.
I lost the two last three sentences. So what you're saying?
If the nodes that have been proposed by Houses sir in the chat, if all of
Uh-huh.
these are correct nodes from the
Mm-hmm.
text that I just sent, from the text that you had just
Mm-hmm.
sent me, if
Mm-hmm.
it is correct, then we can directly eliminate all of our pipeline and build a small direct way and use an API key to build all of these graphs within like a couple of minutes.
Yeah. Yes.
Our
So what?
entire model wouldn't have to like, it's absolutely unnecessary to work
Yeah.
that.
So one thing is that also, one of the challenge which actually Dave I also told you in the graph that we for I mean this is good graph for on the back end data we can keep it, but for visualization purpose the graph you want to see is only the nodes needs to be selected nodes which are coming from a dictionary. So like it has to be genes. So you see, not all the nodes are genes here. There are only like a three or four nodes which are actually genes or the disease, and only those needs to be presented. So this is, I think this is not a rocket science. It's very easy because the way I can provide you the files which are the like a correct nodes could be like what are the possible nodes and what are the possible genes. So once we have that, we can filter it out and then we can actually create the graph. Like you said?
Sir, I'm actually telling something different. I'm telling to
Huh?
just please compare the nodes that have been created by uh, Houses sir and by my BERT uncased model, and please tell how many of those nodes are actually correct and need to stay in the graph.
Okay. So the thing is there are two things here. The models when they are creating a node, they are based on the text. Okay. There is nothing wrong that this should not be a kind of a node. It depends on like what how you are representing those text into kind of a into graphical sense. Makes sense, right? But what I am interested in the tool from application perspective, that all these nodes are not, I mean, even if it is a node just to build a relation on the from the text, but that is not what I want. So what I'm saying is not a right or wrong node. It is about what is right for me. Did you get that? What I'm saying? Because wild type tau proteins. Okay, this is a wild type tau protein. There is nothing like a wrong in the node. But basically, we do not have a wild type tau protein because there is already a tau gene is there, and we want to have just one node for that. So tau protein is there. Then tau, there is another node called tau. Now tau is actually another name for MAPT gene. Okay. So for me, I do not because in this way I will have like a thousands and thousands of nodes in my knowledge graph. and which will not make sense for me from visualization perspective. Again, I'm noticing that you can make a visualization any way you want it, right? I'm not saying it is wrong here. The graph which is showing here is wrong, or the keywords are wrong. These keywords are coming from the text, so there's nothing wrong. What the application we are developing is limited to only those genes and pathways and the disease. Otherwise, we will not be able to make any kind of an insight from those kind of a big graph. They could be in the database. From the LLM perspective, that is fine. You know what I'm saying? So, because let's say when I'm asking a question and I want an answer that like similar to like ChatGPT, AI agent, that can answer me based on the full knowledge graph. Okay. But when we are visualizing that data, did you get what I'm saying? Remember the tool which we are developing? In that tool, we only want to keep the pathway at right now it has only genes, but we can have like a genes pathway and disease in later in future. But right now we'll be focusing only on genes, relation between genes. Did you get that? Dave?
I mean,
April, any comment?
so like I'm a little confused right now. Like that, I mean, how do you want us to proceed right now? Using like the architecture that I proposed, or using just API keys and just open source models to extract keywords, relationships, everything? Because essentially any model would do everything for you. Like when I mean it, like any model, any open source LLM would do all the tasks that I mentioned to you. But the question comes, how accurate?
Yeah.
How accurate is that the open viral version of GPT or Llama, or how accurate is the fine-tuned version of BioBert? Let's exclude LoRa for the time being. Let's how accurate is the fine-tuned version of BioBert?
Yeah,
So I
actually,
guess that is a decision that you need to take.
Yeah, you.
I mean, again,
Yeah,
yes.
yeah, I just want to add that in the field of bioinformatics, I just published a paper on prompt engineering. Like we actually did some prompt engineering work to identify for gene relation prediction specifically. And actually, in our research, if the our we find that large language models can basically outperform classic machine learning or deep learning models in classical text mining, like classical natural language processing work. Actually, I mean, yeah. So why not? Why not large language model all the way and get the results? It's probably too easy.
So throughout my presentation, I've always used large language models. I'm just asking to use a better or a fine-tuned version of a large language models pertaining to a specific task. I never throughout whatever I've been speaking, I never mentioned the usage of libraries like Spacey or Word2Vec or even Globe 7B. Throughout, I've been using BERT, I've been using GPT, I've been using Llama, I've been using Distilbert. I'm just asking to make a more fine-tuned version so that all of the data that we retrieve from these models is more accurate in comparison to what we would have received in other case of a non-fine-tuned model, which essentially comes again up to like the the trade-off between BioBert and just pre-trained or the naturally trained GPT-4 or GPT 3.5, any you may take.
Yeah,
that's the answer.
Yeah, I'm also curious, for, in our corpus, like when is the paper published? I think if the paper is published before BioBert or GPT, because we know that BioBert is a fine-tuned version of BERT, fine-tuned on PubMed articles. So if the corpus is not that new, BioBert is probably already fine-tuned on it. Also, GPT, they have their training corpus is much larger, probably including archive, bioarchive, those publicly available data. So we can probably also presume that if the paper is not that new, both BioBert and GPT has seen the paper. So there is probably not that necessary to fine tune it again
then I guess what you're proposing is to just use BioBird for our tasks, like a direct proposal that we had developed over here. Give BioBird a query and directly ask it to build the knowledge graphs. Is this pipeline correct?
Yeah. So I think, in my understanding, BERT is an encoding, is an encoder, is an encoder only. And when you give it the query, the output, I mean, the direct output of BERT is just vectors, right? A matrix of vectors. And we need to like post-process that matrix to get what we want. And I think this post-processing is non-trivial to post-process that matrix into a knowledge graph. What do you think?
I'm still
So,
this communication gap.
So I think that
what is it that you're proposing? Like,
so
to give it something
let
other
me
than
I think Yibo, thanks for actually providing this insight, because that was actually my main purpose behind setting up this collaborative meeting. That what I'm interested in an application where I can like develop a knowledge graph. Basically, it's a kind of a application for scientists to get a more precise knowledge or information about the question which I'm asking. So let's say, and the chat GPT is not sufficient for that thing. And in order to do that thing, one thing we want to know that, let's say, whenever there is an outcome, let's say that application is developed, and I ask a scientific question to that, and then it actually gives the chat GPT like output. It asks all this, also this. But I want to also make sure that all those answers coming from this application are actually sentences which are coming from certain paper. It is not like a made up of a story. That's the one thing. Second thing is that I want to take all those sources of all those publications and try to connect, see them into the network form, so that I can overlay some other kind of bioinformatics data on that. So because this is just a kind of a network based on the literatures, but then I can have some, let's say, additional information data, compound data, or disease data, or differential expression data, or any kind of those databases. Then I want to map this. So it's more like a visualizing those network to make a certain outcome of that thing. So I want to have this kind of a application, which is a kind of a combination of these two things. It has a GPT-like response, and at the same time, we can visualize a network where we can map the data more like from infographics way.
Okay, now I understand. So I think like the major output is actually the knowledge graph, right? Not the final response.
No, I want not binary file, but I want because one thing is that the GPT like outcome is very good. It's a very like a human like interaction. You can ask human like questions and it can answer you in a way so that you can understand it. Graph does not answer you, right? You can ask questions. Graph can simply highlight the things, but it cannot answer you in a human like kind of language, right? But the advantage of the graph is that there is a huge amount of data. It's like a protein-protein interaction data, right? You can see the network, you can identify the modules, and then I can find out, let's say if I have network, I can find out the disease modules. And from disease modules, I can identify the which pathways are enriched. And then I can go to those kind of pathway gene set enrichment analysis, GSEA. I can do that thing. So that lot of bioinformatics kind of analysis, which I want to do along with LLM like output. Do you know what I'm saying? A combination of these two.
Yeah. So I think what we need the most is probably the large language model agents to like highlight the graph. Also, probably if possible, give the final response to the query. Right. And I think the gap for now is probably we don't have a very high quality knowledge graph, and that's what Dave is working on.
Yeah. So actually, the high quality knowledge graph. So I have another team of people who can actually provide the high quality knowledge graph data. They have actually knowledge graph data into Neo4j. They already created that. I can get that data. So, but this is just a data, which is like a build. I not. I mean, maybe next time I can set up a meeting and they can actually show you how the data is. So more like a structured data about the knowledge graph, which is created or generated based on not just a literature corpus, but many other sources.
Okay,
Do you know what I'm
I
saying?
see. Yeah, I see.
We can utilize the data. I'm right now actually, I think I showed you, right, that we are working with EGA on developing an application. And in future, not now, this is why actually this LLM based project, which I started, is a kind of an initiative, a new initiative. We want to develop a kind of application as an independent of the project with EGA. But in future, like I would like to see if this is something could be integrated as together.
Yeah, that sounds exciting.
Yeah. So yeah, so I think this is what we are interested. I'm interested to know further, and maybe we can find a better way solution to solve by working together. Do you think, Dave, Ivo?
Yeah,
I
sure.
think
I
Jose is
mean,
already.
yeah,
Sir, I
I
would
guess.
appreciate your insights into this. Like, due to some reason or like a communication gap, so I couldn't really understand like what you are proposing. So, like, are you proposing like this methodology that's on my screen right now? Like this one? Like,
Uh,
is it this that you're saying that we need to give our query directly to the Llama or GPT and then it would give us the knowledge graphs? Or is it something else that I couldn't get? Because I was reading the blog that you had sent, and even in there, like Rahul sir says ki you need to establish an RAG pipeline that would essentially give a specific set of prompts to Mistral 7 billion and Zephyr models and create the knowledge graphs accordingly. I again have this one knowledge graph as well for you. If I could share off my screen, now this was built using GPT, a pre-version of GPT 3.5. I'll share off the full version of my screen so that I'm able to make sense actually. If you can see this file, I'm sure Gyan sir has seen it many times. Like this one is actually wherein I give GPT a Wikipedia page. This is like common sense question answering dataset. It is nothing fine tuned. We do not care about accuracy. We need to understand how GPT needs to find out. GPT finds out notes and everything. This is this how you want things to do? Because this was created using just one line of code and this pretty simple to make. And I would be the like happiest if we can just work it off this way.
Yeah.
Because this was
I tried to extract knowledge graph from like hundreds of literatures using this way, and actually the first of course the results is not so good because usually specifically the recall is good, but the precision is not that good, which means in most cases, just like what Dr. Srivastava mentioned, it will extract the same node multiple times and it will treat it as like different nodes. So it makes the knowledge graph looks very messy. But what I'm trying to propose is indeed doing it this way because it's much simpler. And I'm mostly working on it from informatics point of view, and I think you are doing it more from a computer scientist point of view, right? You are trying to make it faster, make it efficient, evaluate all the possible solutions. And what I was trying to do is just find the easiest solution and get it to work. So what we did is, even though the knowledge graph extracted from those literatures is not good, but we can post-process those knowledge graphs. Like there are actually a lot of BERT variants like BioBERT. If you know, there are also something like USMLE BERT, where you can use that embedding to merge those, how to say, duplicated nodes. And after merging, it's possible that we can treat that knowledge graph as like treat those knowledge graphs as a perfect representation for those literatures, and we can use a large language model agent to query that knowledge graph.
How do you want to do this backtesting? Like,
To-
let's say you're creating the knowledge graphs using the large language model, a complete untrained large language model. Let's say cloning it with an API key. How do you want to do this backtesting about verifying whether the particular knowledge graph has the correct nodes or not?
I guess it will be very hard to like to directly verify that results. I mean,
So they
how do you?
would actually mean like manually screening all of those knowledges, all of those
I-
graphs, because
um,
I've seen the data that once Srivastava, but Gyan sir, when he provides them, it consists of around more than around like 1.5 million nodes. A graph encompassing that much amount of data is completely like impossible would be just a word, but it's very difficult to analyze all of those specific nodes and then decide as if which node is actually correct or not if it were
Yeah.
made through a process that comes directly without any fine tuning.
Yeah, I guess that's the problem with text mining. I mean, how do you plan to to validate your methodology? Like, I know you have.
I don't plan to re-verify my knowledge graph. I plan to build my knowledge graph fine-tuning the model. Like what you are telling is first build the knowledge graph using the standard LLMs locally available, and then like improvise on this built knowledge graph by verifying the nodes built if I have received it correctly.
Yeah, that's exactly what I'm saying.
Okay. What I am doing is making these models, I'm fine-tuning these models into creating the perfect knowledge graphs which have a higher level of accuracy of being of having the correct nodes than the ones that were built by a non-fine-tuned or a non-pre-trained LLM. This makes things different because this has a higher accuracy of being correct and like specific nodes rather than the previous one.
Yeah, but
like if I was able to like make some sense using my hand signals, whatever.
Yeah, I can understand the point, but then
architecture.
I mean, you are doing this with probably some online training need to be implemented because new literatures are coming out every day, and we probably need to fine tune that model every day. And if we do it in my way, we need to update the knowledge graph every day. So that's, I mean, so I guess like, there's no perfect solution for this.
Online, so could you just once share of Gyan sir or Bhupesh? Anyone just share of that once that entire graph wherein we have all the genes? Like Gyan sir could do it, or we have Bhupesh also.
Say again, what the question you're asking? Say again.
So if you could just share of the screen or the nodes and their first order graphs. Gyan sir is also there. Bhupesh is also there, who is our tech team. So I mean our backend developer team. So if anyone could just share of that, it could have been much more easier, I guess, for you also to get.
You are saying that all the genes, is that you are saying all the genes known?
No. The graph that you use to show using Neo4j, or the one that Bhupesh, so just give me 1 second, I'll call up Bhupesh as well.
He's here. I see Bhupesh is there.
I'm here.
Yeah.
I'm just okay.
So
Mute,
yeah.
I'll just take a few notes and like represent that graph. Just a minute.
Just once share your screen and present that graph once.
Yeah.
It would be much more
on it.
I guess understandable for both of us. What are we dealing with? The amount of data.
Just a second. I'm getting some notes. Chain information.
Random एक बार 300 notes लगा के देख.
So
in first order,
now one thing is that in the while Bhupesh is working,
50 genes, you will get around more than 10,000 nodes in total.
Yeah, just share your screen while you do it, no?
No, that will be too much. Visualization will collapse. And also, at that point, so you know this the in this application you cannot solve all the problems, but we can be little smart in that way. That it is not necessarily that we want to visualize the full graph, knowledge graph. Okay, now I'm using the word little knowledge graph and the graph, two different words. Knowledge graph could be like a very complex graph information which has every information about the biology of the disease. Okay, you can ask any question, it's like everything. The graph which we want to visualize could be just a small set of the content of the knowledge graph, which is meaningful for visualization purpose. It's like just a kind of short version of that thing, very short version of that. Do you think, Dave, this makes sense, Yubo? Because
Yeah.
there is a reason at some point, because let's say if I'm a scientist, I have a question which I want to ask, and I want to get a more insightful answer from the model. That means that model has a full information on the back end. It's like a full knowledge graph. It knows everything. Okay. But what I'm visualizing, because I have some additional type of data I want to map onto that graph. And so in that case, I don't need the full knowledge graph. I just need all those genes. So this is actually, let's say, for example, this knowledge graph. And at this point, this knowledge graph in any way for scientists for discovery, it will be very challenging. I am actually so glad to see, I tell you, that this itself is a big achievement, that this 8,000 nodes, we're able to render it. Because I do not even know there's a bioinformatics tool which can even show at that level capability. But the problem here is that this will not be helpful from the analysis or from insight perspective. Finally, we want to explore this network, not just visualize it. You know what I'm saying?
So,
Looking at it.
If you would allow me to intervene for just 1 second.
Sure.
What you are seeing on the screen is the total amount of nodes available. No scientist needs to see.
No. The total amount, so this is where actually, so let's say, for example, if you ask me how many words are there in the dictionary, there are like almost 1 million words. But how many words are there in your graph, what you are showing in the online, the Barack Obama? Maybe 20, 30, right? But the total number of words, actually, dictionary is million. Right? What you are seeing right now in this graph, maybe this 8,000 node, these are 8,000 node which is seeded around the seed which Bhupesh gave as input. It is only those genes which are connected to that one. The actual number of total genes are around 50,000.
Okay, so like even to answer that question, so Bhupesh gave a set of genes, and these are all the nodes connected to those set of genes. Am I correct in understanding this?
Yes, okay. Yes.
When this gives a particular gene, he will get the nodes connected to only that one gene, right?
Yes.
Perfect. So this is the set of all the nodes connected to 100 genes that Bhupesh gave right now.
Yes.
Considering that we built this same knowledge graph, not the same knowledge graph, a different knowledge graph using LLMs.
Yes.
Now the two options that you have in hand are either you can fine tune the LLM that is building these knowledge graphs, like that you can do you have to do at regular intervals, since every single time, like every day, millions of literature is being published. Or the second option is use a standard LLM that Yubo just proposed. Use a standard LLM to build these knowledge graphs and then check from this graph which node is correct and which is not, and manually drop it. So the choice is yours.
Actually, I was not proposing to manually drop it. I just want to. I'm sorry to interrupt. Yeah.
We can. When I say manually, I don't mean like choosing one by one. I mean algorithmically, like making a program or something like that would go through the nodes and check which is right or wrong. Am I correct?
Yeah, kind of. We're actually developing this. Let's say
online
platform.
I understood from what you told. You're always free to correct me.
Yeah, I mean, we're actually using some methods like neural gas. You probably have heard of this. So when a new node or a new example come in, we consider whether it already exists in one of the nodes, and if it is, we'll merge it to an existing node so that both the nodes and the relation. I mean, we are talking about the graph, so I would say both the vertex and the edge does not get too messy. So that's what we are working on. I mean, yeah, if that makes sense.
Sir, I'm just confused with a little part. Are you developing the software that would manually go through this knowledge graph and verify each of the nodes? I mean,
you're asking me or you're asking Yubo?
Yubo, sir.
Okay.
Yeah. Actually, this process can be described as we are not like developing an actual application. We are only talking about the algorithm, like how to cluster similar nodes. Like that's the point. how to prevent the nodes get too messy. Yeah.
Understanding whatever like I understood, like during the course of the time that I've spent, it was fairly difficult enough to verify the nodes from the knowledge graphs than it would be to tune in the models directly that would be building these graphs. This was completely my understanding, and I am free to criticism or free to understanding how things would be different. So if you say that you have been developing this software that can actually go through the nodes of the graph that has been developed for the, I can see there are like 8,000 or even more such nodes in the graph that is being shown on our screen. So if you already are developing or are close to completing the software that can verify the nodes on this graph, then I guess we are pretty good by using just the API key of GPT.
So now there's a lot of here gaps here. First of all, what the graph here is showing, what is this graph here? Does it have any kind of anchored question? We do not know. So this is, I mean, multiple pieces are there. Like one piece which Bhupe is showing that if you have a seed list of genes, there is an algorithm which can create a network based on backend of network data. It's just that, okay? There's nothing more than that. But the advantage of this thing is there that there could be a scientist can map the additional data which they generated in the lab onto this thing. So if they have some extra information beyond the literature, they can map it here. For example, let's say scientists did some experiment in the lab, and now they know that which genes actually shows a certain level of changes in the particular disease or not. They can actually map that data here in terms of color and size, like the fold change or FTR. Those are some statistical numbers. Okay. Now, this kind of things are not there in ChatGPT. ChatGPT can give you answer of from the backend data what it learned, but you cannot say, okay, I have my data. This is my Excel sheet. I know this gene accelerator. Can you show me how it matches with that thing? At least that thing not there. Second thing, now you can see whenever you have graph like this visualized, there's some cluster formation. So there is a whole network analysis field which actually try to bioinformatically to a lot of like developing method where you can make sense from the biomedical data. Okay. Now what we are trying to do here, we are trying to see that whether we can enhance this kind of application for scientists, biomedical scientists. Think about that. I am a biomedical scientist. Okay. What I'm interested, is there any application which can be like a god for me? ChatGPT is like a god for me. Okay, like you have seen that scientists like so much ChatGPT because you can ask anything and it answers. The only problem is there that I'm a scientist. I need a more specific and true answer rather than hallucination. That's the one thing. Second thing, whenever there is an answer coming, I want to have a proper authentic sentence coming, not like made up story. That means if ChatGPT or my application answer, oh, Parkinson disease has a PINK1 gene as one of the best target involved in lysosomal pathways, I want to say, okay, where do you find this information? Tell me. Then it should point me to the right direction. It should be that paper, the link of that paper also should be there. Okay, that's the one thing. So my application needs to be very reliable. Second problem will come that when I ask a question, which is very like a very complex question, the application will give a lot of literature also, right? It will give me like 100 different literatures as a backup to answer my question. Now, what my question will be, okay, what are those genes and pathways which have been mentioned in those 100 different literature? How those genes are connected? Are they have any physical protein-protein interaction or not? To do that thing, I need that data into the graph format so I can map it in this application. Did you hear what I'm saying? Yibo?
Yep.
And Dave, are you getting something like what I'm trying to do? So it is up to you, like computationally, how prototype you want to do. Think from the user perspective, what I'm interested in. I want to make a scientific discovery. Okay, scientific discovery you can make not by reading already existing discovered literature, rather than you read. So like as a scientist, if you want to make a new discovery, you want to publish a paper, you do not publish a paper of something which is already published. ChatGPT gives you answer of what is known. It does not give you, it cannot replace a PhD student because ChatGPT now can have its own discovery. It cannot do that thing. So in order to have a new discovery, you can do that when you have some data which has not been analyzed the way it could be. Even if it is a public data available, maybe some literature, they generated some maybe RNA-seq data, some data on the postmortem brains, and they publish a paper, but you can utilize same data to have your own insight, develop a new method, you analyze the data differently and make a new discovery out of that. That is possible. That is why data is important. ChatGPT does not help you to put the map those data onto the kind of answer it gives you. So what I'm trying to do as a scientist, I want to see an application where I can bring advantage of both together. Did you get? Right now, this application which I see visualization, it is on data, but it does not have insight from literature. Did you get what I'm saying? The only thing which you see that there is an experiment where the two proteins are physically interacting or not, it is connected here. But now I want to see that how much literature or LLM knows about these two proteins here. How much things are known about the disease here. Can we have that information here? Did you know what I'm saying? Ibo and Dave, did you get at least partially some what I'm trying to say?
Yeah, I can get it.
So enhancing, it's like that LLM is very powerful. Definitely that is the thing. But as a scientist, if I can find an application where I can get the advantage of LLM like ChatGPT, on top of that, I can also do some bioinformatic analysis coming out of the LLM results that will enhance my learning and make it my discovery more smoother. So it's more like we are discussing the ideas about like a new kind of application which could be very helpful. And that application will be about like this is there why I bring the concept of knowledge graph plus LLM. But I think that one thing here, you whenever you both use the word knowledge graph, they mainly is like a relations and or like nodes. Obviously, graph is always node and edges. But when I use the word knowledge graph, like basically I'm talking about networks. Um, the, okay, let me take my sentence back. There are two types of like we need to address the graph in two different level. One is the graph which we are visualizing the data, like you are seeing in the screen. Okay, this is not knowledge graph. Okay? This is not a true knowledge graph. It is just a like a two genes and the interaction amongst them. So every node is a gene here. Okay, if you go to the text, the every node could be there, multiple type of entities could be there. Okay, like if you do the LLM, the nodes could be of many different type, not just kind of gene itself. So this is the visualization part here is actually a very short and a specific class of nodes, which are actually just a small set of knowledge graph. Making sense? Like, do you think am I correct on in that or no? So if I ask, okay, build a knowledge graph for Parkinson's disease, that means with the LLM and AI, I can build a kind of a very humongous knowledge graph where the nodes and relations are everything about the Parkinson's disease. It's a pathway, chemical compound, it could be anything. As long as anything is related to Parkinson's disease, it might be there in the knowledge graph, either in the form of edge or in the form of node. Right? That will be very giant knowledge graph, which could be very helpful in terms of answering my human-like questions. Like I can ask, interact with the knowledge graph. Like I think I showed you the application also, right? There's a Chat GPT like we have another group which has developed a research assistant where actually you can ask any question like Chat GPT and it will answer you based on the knowledge graph. That's a huge knowledge graph. For visualization purpose, it's a kind of a very small portion of that knowledge graph, which is pull out only those nodes which are which are assigned as a genes, and see how different genes are connected. The two genes might be interacting because knowledge graph has found certain relation among them, or these two genes might be interacting because there is a scientist found an experiment, they found that these two protein complex they binds, physically binds. So there could be many ways the two genes could be connected. So I'm interested to render that part here as a knowledge graph so that we can actually add on top of that more data for analysis purpose, which goes a little beyond LLM model. Did you get that? So at some point, it's like a graph, knowledge graph, LLM, and visualization. This is the kind of things, it's in the middle of these two. This like it's a kind of a balance of these three things together. I think I sent you a link for, it's not that we are doing something totally new. We are doing something really state of the art. Definitely we are doing new thing, but similar effort, people are trying to do this thing. It's not that people are not, people have been trying some very similar things. And there's a software, there's a company called Causally. I think I sent a link, I'll send a link to you as well. They have developed something similar. So, but it's a simple. We want to have more stuff. Actually, we were about to buy the license for the software, which does simple form, but we can do much better than that. I'm going to send you the link to you both, okay, and Jose also, and then you can see. So you'll get a little more idea about like how people are trying to do something. Not exactly this thing. Different people are trying in something. They are thinking in this direction, and maybe we can brainstorm a little more ideas like how we can do better than others. Like he said.
Yeah.
Yeah. What?
Yes.
Obviously, and I like the idea you brought that if something could be done in a simple way, the same effect, we want to be smarter in that way. Because this is more like it, because then we can achieve few milestones faster than things, and then we can always have a kind of a exploratory part in our work which can keep on going. At the same time, we can have certain like a demo part also ready. So what I'm trying to say here, that it's not that we do not want to do like fine tune ourselves. We need to be a little practical, that sometimes, let's say if you need a lot of resources to fine tune certain things because you are training your own data, okay, so while we find that way to tune our data, we find a server, we get the right data. Well, it's more like its own PhD proposal. We can have a shorter version, or we can apply LLM model, like the way Dave and Jose is saying. So we will have both ways. There's nothing like right and wrong. They both have pros and cons. We just want to see that take a balanced advantage of both kind of strategies.
That makes sense, sir.
Okay. Yeah. So maybe next weekend, Yubo, do you think that this is a good idea to meet on weekend and have some brainstorming ideas? How can we work?
Yeah, sure. It sounds good to me.
Yes. Yeah, and could you please send your paper to Dave, the one you published, so maybe they will get a little more understanding, like what kind of background you have.
Yeah,
So,
yeah, but that I just want to add that paper is probably totally irrelevant to what Dave is currently working on. It's more on
yeah, but it will be good for him to have a little bit of context of the background, like the background you have, and what kind of things you have done. And then in future, like we can brainstorm. So remember, like when we discussed with you about the something I want to develop, and then we say, okay, we could think about how to solve the problem. And then today was a good start, but maybe we need to further polish it about like how we should build the application, what should be the prototype for that application, and then we can start working on that part.
I definitely think this is a good starting point. Anyway, we can at least we can compare different methodology on this project. So.
Yes. Yeah. Cool. Yeah. So nice. Yeah, I think it was good. We'll meet up again maybe next week.